It's my pleasure to introduce Pavel Etingof of the Massachusetts Institute of Technology, who will talk to us today about D modules on Poisson varieties and Poisson traces.
So it is my pleasure to speak here at the Worldwide Center of Mathematics. It's my first visit here. And I will speak about joint work with my collaborator, Travis Shedler. And what I will talk about is contained in the paper on the archive 0908.3868. So actually, I want to tell you about Poisson traces, which is really what the final results are about, and also about applications to representation theory. And then I will explain how to prove the results, and the proofs involve D modules. So, so first let me remind you what Poisson algebras are. So definition, Poisson algebra over some field K is a commutative associative algebra. Let me call it A over the field K, equipped with a Lie bracket from A cross A to A, which is a derivation in each variable. So this last condition means that ABC equals to ABC plus BAC. And the algebras that I am interested in are algebras of functions on algebraic varieties. So I will make another definition, which is an algebraic variety X is a Poisson variety if the algebra of functions on X in the affine varieties case, or sheaf of algebras of functions in general, so structure sheaf, is a sheaf of Poisson algebras. So this is a local notion, and for affine varieties, which is what I will mostly deal with, it just means that the algebra of regular functions on X is a Poisson algebra. So now I want to say what a Poisson trace is. So it's again a definition. A Poisson trace on a Poisson algebra A is a linear function, which I will call T from A to K, such that T of the Poisson bracket of two elements is 0. So that means that T is really a function on the quotient space. we can think of T being an invariant function because we can think of the Lie algebra A acting on itself, and then this condition just means that T is invariant with respect to that action. And so the space of Poisson traces is this, which could also be interpreted as the zeroth cohomology of A with coefficient in itself in the sense of Lie algebras. And the dual space, well, this space is dual to the space, which is this space, the quotient of A by the span of all the Poisson brackets, and this is the zeroth homology of A with coefficients in itself in the sense of Lie algebras. And one also refers to it as zeroth Poisson homology, HP0 of A. So this is called Poisson homology. This is the zeroth group of some homology theory for Poisson algebras, which I will not define. So an interesting question which I'm going to deal with in this talk is when is this space finite dimensional? Where by this space I mean really this space or its dual. Of course, they're finite dimensional simultaneously. Well, let me give you an example to be more concrete. Well, suppose V is a finite dimensional symplectic vector space over the complex numbers. And G be a finite group of symplectomorphisms of V. Linear symplectomorphisms of V. So then I can look at the algebra of regular functions on V, and this is going to be a Poisson algebra in a very simple way. I mean, if you have, if the symplectic form is the summation over I dxi dpi, then the Poisson bracket of two functions is just the sum over I df dxi dg dpi minus df dpi dg dxi. Where these are both in this C of V. And also the invariance C of Vg contained in C of V is also a Poisson algebra. This is the algebra of functions, regular functions on the quotient V over G, which is an algebraic variety. So we could say that this quotient V over G is a Poisson variety. And so one might ask a question whether the space of the quotient space like there for this thing is finite dimensional. So the question was asked by Alev and Farkas is the space HP0 of the invariance finite dimensional. And what is its dimension? And the answer was given by Berest, myself, and Ginsburg. And the answer to the first part of the questions. So HP0 is finite dimensional, but we couldn't answer the second question, and in fact, very little is known about this. So this is a big question. What is the dimension of this space? Well, I mean, the data is a finite group and a symplectic representation of that group. And given that data, which is a data for representations of finite groups, you're supposed to produce a positive integer, or a non-negative integer. Well, actually, it's always positive, which is the dimension of this space, and nobody knows what it is. In some cases, we know the answer, and in those cases, it is rather hard to prove that the answer is what it is. In general, it is not known, and this is currently under investigation in my joint work with Travis and some other people. Well, yeah, I mean, it's a Poisson homology, but I will interpret it. So this is exactly the reason why this problem is not so trivial is because this definition is somehow non-local with respect to V. So it operates with functions defined on V globally, and not it doesn't operate locally in neighborhoods of points. And so what I will there is actually so a more general question would be: is this true if a symplectic vector space is replaced by a symplectic affine variety? So the reason this space is poorly understood is because we didn't have before this work a local picture for this. And what I will explain that in fact you can develop a local theory for it, and this is done in terms of some D modules, and then it will be actually a cohomology of a certain D module. And this D module will be holonomic, which will imply that the space is finite dimensional. Okay. Maybe I should give you another example to show that this finite dimensionality is not so trivial. So let's say X is a symplectic affine variety. So this means it's a smooth affine variety, and we have a closed non-degenerate 2 form. Its differential is 0. And then the Poisson bracket, then this is a Poisson variety with the bracket given by a very simple formula. We take df tensored with dg, and we evaluate it on the inverse of omega, which is a section of the tensor square of the tangent space, tangent bundle. So in this case, one can show, it's not very hard to show that HP0 of OX is just the top cohomology of X. Where by top cohomology of X, I really mean the cohomology of degree equal to the dimension. So maybe I should say that this is connected. And then it has a certain specific dimension, and as an algebraic variety, and top means the cohomology of that dimension. So this is really middle cohomology, because real dimension of that variety would be twice as much. But it's known that for affine varieties, cohomology doesn't go above that degree, and in that degree we get a certain space. And in fact, well, you get that it is the top de Rham cohomology, which means you write the algebraic de Rham complex, and this is the top cohomology group of that complex. And it's not obvious from the definition that it's finite dimensional. Actually, Grothendieck proved that that cohomology is the same as the usual cohomology. But this is a non-trivial theorem. And so, in particular, it's not obvious that it's finite dimensional. But it is, because of this Grothendieck theorem. And in fact, this can be proved in a more elementary way, but still it is not completely obvious. Are there any questions? Okay. So now I would like to give you some results which generalize this theorem, in which we obtained with Travis. And to state this result, so this is a special case of some more general theorem. So let me call the theorem 1. And so to state this more general result, I'm going to need to define what are symplectic leaves. So definition: a closed Poisson subvariety of Poisson variety X is a closed subvariety Y in X, such that the ideal of Y is invariant under Hamiltonian vector fields, which I will call VF. And this is really F bracket something, where F belongs to OX. So this is called Hamiltonian vector field. By the way, I'm talking about varieties which are not necessarily smooth. And in fact, as I will explain a little later, in essentially all interesting cases for me, they will not be smooth.
Isn't that the only interesting case for any space?
Yes. Well, I mean, it could be interesting to consider the smooth varieties on which the Poisson structure has some singularities. Anyway, so what are these Hamiltonian vector fields? So I told you that Poisson's bracket means that any element of the algebra defines a derivation. And this derivation in the geometric setting is a vector field. So what I said is really for affine varieties, and if the variety is not affine, then instead of ideals, you should talk about sheaf of ideals, and so on. So I'm not being careful about that because it is well known how to do this, because all constructions I'm going to do are going to be local. Okay, so this is what it means to be a closed Poisson subvariety. And then a symplectic leaf. Well, symplectic leaves in general are, so in ordinary smooth C-infinity Poisson geometry, they are defined in the following way. Symplectic leaf is the set of points where you can move by Hamiltonian flow from a given point. But we are in the realm of algebraic geometry, so we should, what I will define is not, so you can define, for complex varieties, you can define symplectic leaves as holomorphic subvarieties, but non-algebraic ones in the way that I just said. But I only care about algebraic symplectic leaves. So I will say an algebraic symplectic leaf in X, in a Poisson variety X, is a locally closed connected smooth subvariety Y in X such that Y bar is a closed Poisson subvariety of X for which the Poisson structure is symplectic on Y.
The locally closed and the closed that you're using in the Zariski topology? Or the
Yeah, Zariski. I could do it in analytic topology as well. At this point, it is not important. This is still less general than the symplectic leaves which we define in usual C-infinity geometry, because in C-infinity geometry you can get some analytic subvarieties which are not locally closed. For example, a winding of a torus or something like that. And this is not, I'm not allowing it here. So what do I mean by the Poisson structure being symplectic on Y? Well, symplectic on Y and not symplectic outside, but not on a bigger, but not on a bigger subvariety of Y bar. So the idea is, so what does it mean? It means that if we, so on Y bar we have some Poisson structure, and if we take any affine open set that is contained in Y, then on that set the Poisson structure is symplectic, which means that it comes in this way, like here. And we say that X has finitely many symplectic leaves. If it is a disjoint union of finitely many symplectic leaves. So in this case, we have a kind of stratification of our variety into symplectic leaves. And so the Poisson structure in that case can be understood in terms of that union. So a kind of symplectic on every stratum of this stratification. So maybe I should give you an example. What happens for V over G? So V over G is an example of such a situation. So example, so suppose V is as before and G is an SPV. Then a parabolic subgroup let me call it H in G, is the stabilizer of some vector in G, and then symplectic leaves of the quotient V over G are labeled by conjugacy classes of parabolic subgroups. And in particular, there is finitely many of them, and they form a nice stratification, like I say here. So how are they labeled by these conjugacy classes? So basically, we should stratify V with respect to stabilizers of points. If I fix a parabolic subgroup, then the set of points, we can look at the set of points that are fixed by this subgroup, which is a linear subspace of V. And then we can look at the set of points which is fixed exactly by this subgroup, which means that the stabilizer is exactly that subgroup. And that would be an open subset in this subspace of V. And then we look at the image of such a thing in V over G, and that would be a symplectic leaf. But if you take a conjugate parabolic subgroup, the image would be the same, so it would be the same leaf. And one can show that this is indeed a stratification of this space V over G into symplectic leaves. So let me give you an example of sort of a sub-example of this example, which is the simplest one. G equals to Z2, the cyclic group of order 2, and V equals to C2. And the action of this group on this space is by minus the identity. So xy goes to minus x minus y. So then V over G could be, which is C2 modulo plus minus 1, can be identified with the usual quadratic cone. This is the so-called A1 singularity. This is the simplest singularity that exists. And what is this singularity? Well, I mean, what are the invariants under this action? So we have x squared, which is A, xy, which is B, and y squared, which is C. And they satisfy the equation AC equals B squared. So this is a zero set of a quadratic, non-degenerate quadratic form in 3 variables. Looks like this. The real locus looks like this. And so there is a Poisson structure on this. This is a singular variety with this A1 singularity. And the Poisson structure on it has 2 symplectic leaves. One leaf is this point here, which is the point 0. And the other leaf is the rest. Over real numbers, there are actually 3 geometrical leaves, which are the upper and lower semicone. But over complex numbers, this is the same thing. They are connected with each other. I should mention as a remark that all examples like that, which is what I will care about, finitely many symplectic leaves, will necessarily be singular unless they are symplectic. So if X has finitely many symplectic leaves, but is not symplectic itself, which means it has more than one leaf, then it is necessarily singular. And the reason is that, well, I can say without writing what the reason is. If you had a smooth variety, which had finitely many symplectic leaves, then in particular, it would have an O. So there would be, let's say it is irreducible, then it would have one leaf of maximal dimension, which would be open. And the complement would be a union of leaves of smaller dimension. And because they are symplectic, they would have to be of codimension at least 2. So we have a symplectic non-degenerate form on an open subset of our smooth space, or such that the complement has codimension 2. And so if I take the determinant of this form, it's a function. Well, it's not a function, a section of a canonical bundle, but anyway, locally a function, which is non-vanishing on an open set whose complement has codimension 2. And then by standard elementary result, it has to be non-vanishing everywhere, because a holomorphic function or a regular function cannot have zeros in codimension 2. So that's why it has to be necessarily singular. Okay, and so now I can formulate the main results. So theorem 2. So this is my joint work with Schedler, and it says if X has finitely many symplectic leaves, then and let's say this, so X will be an affine Poisson variety. Then this space functions on X modulo Poisson brackets inside of them is finite dimensional. So moreover, if more generally, suppose we have phi, which is a map from X to another affine variety Y. So if this phi is a finite morphism, which means that we pick a subalgebra in OX, finitely generated, over which OX is a finite module, then OX over OY OX is finite dimension. Again, we do not claim anything about the dimension. We don't know how to compute this dimension. It's a very hard problem in general. But at least we claim that it is finite. So a corollary of this is the following, which is a generalization of the theorem of Beres, Ginzburg, and myself, which I mentioned before. And it says that if X is symplectic, and G is a finite group of symplectic transformations, of X, and now I do not require that X is a linear space and that G acts linearly anymore, then OX over OX over G OX is finite dimensional. And in particular, if I take OX over G over its commutator with itself, then this is finite dimension. So this is, if I take X, so the reason this is a corollary is that we can take Y to be X over G. Then we have a map. This has finitely many symplectic, well, X has finitely many symplectic leaves, and the map from X to X over G is finite. By the way, it's not required here that Y is a Poisson variety. So this is well, the Berist, Ginzburg, and myself theorem is this special case of this when X is a linear space and G acts linearly. But it's true also in the nonlinear setting.
Can you explain what does it mean that it's finite? How we call it? It's not finite dimensional. So this is because in many sub-varieties there or something like this. So they don't formulate it clearly. Maybe. So they don't formulate it clearly. I just wanted to understand what does it mean that does it mean that it's finite dimensional, unlike this bigger basic variety when we have X.
Yeah, so it's the fact that it's finite dimensional is basically related to the fact that you have finitely many symplectic leaves. For example, this fact could be related to the fact that you have finitely many symplectic leaves in X over G. So basically, the idea is that you look at the maybe it will be more clear if I formulate a C infinity analog of this theorem, which I was going to do anyway. So let me give you a C infinity version. So let's say X is a C infinity, compact symplectic C infinity manifold. And G is a finite subgroup of symplectic diffeomorphisms. Then I can look at the following thing. So I look at C infinity of X G. So let's define E is the space of distributions on X which are G invariant and stable under Hamiltonian flows with a G invariant Hamiltonian. So I look at distributions on X, generalized functions on X, which are, or generalized measures, which means distributions on the space of C infinity functions, which are, first of all, G invariant, and secondly, invariant, or actually you don't even need G invariant, which are stable. It's enough to say they are stable under Hamiltonian flows with respect to G invariant Hamiltonians. Then E is finite dimension. And actually there is a formula for the dimension of E in terms, if we know something about fixed points of the section, and we know the dimensions of this space in the theorem of Berist, Ginzburg, and myself, which we don't really know, but if we, just denote it by something and plug it in, we get an answer to this problem. And the reason basically is the following, that if you look at X over G, it's kind of a symplectic orbifold, so it has these symplectic leaves. And we have basically these distributions are some kind of delta functions sitting of those leaves, but since there is finitely many leaves, it is finite dimensional. But you don't only have delta functions, you have some derivatives of delta functions, second derivatives, and so on, and you don't know how many derivatives you will take, but it turns out that there is only finitely many derivatives that are allowed always. So this is basically the feel, the essence of this theorem. Okay, so maybe I should also give an application to representation theory. So let's say A is an algebra with ascending filtration. So F0 of A is contained in F1 of A. Let's say this is just C, F2 of A, and so on. But it's an exhausting filtration, but I don't assume that it's commutative. So typically it will not be commutative. And let A0 be the associated graded of A, which is a direct sum of A of I plus 1, so Fi plus 1 of A over Fi of A. And suppose that this is commutative. So a typical example to keep in mind would be something like the universal enveloping algebra of a semi-simple Lie algebra divided by the ideal generated by a central character. And in this case, it is known, so A is kind of deformation of a commutative algebra, so A0 has a Poisson structure. So this A is a quantization of A0 with this Poisson structure. So this Poisson structure is obtained from the multiplication in A. And suppose A0 is functions on some x. Well, this x could be a variety, but it actually could be also a scheme, which means we allow nilpotent elements, affine scheme. Or also formal scheme is okay. So in fact, there are more general versions of what I said than just varieties. Suppose we have this thing, so this would be a Poisson variety or something more general like that. And suppose X has finitely many symplectic leaves. In these generalized settings, there is also a notion of having finitely many leaves, which I will skip because it's kind of straightforward to define. And then the theorem is the following. Yeah, if you were looking at it's okay. Yeah. So the theorem is that in this case, A has finitely many irreducible finite dimensional representations up to isomorphism. So this is something that we want to know in representation theory, that a certain algebra has finitely many irreducible finite dimensional representations. For example, if you take the universal enveloping algebra of a semi-simple Lie algebra and mod out by a central character, then in fact it can have only one non-irreducible finite dimensional representation at the most. And this is well known from the representation theory of Lie algebras. In that case, this condition is satisfied because X is the nilpotent cone of this Lie algebra. And the nilpotent cone is a Poisson variety which has finitely many symplectic leaves, which are the nilpotent orbits. But there are, enveloping algebra, therefore, is not such an interesting example, but there are algebras which give you more interesting examples, such as, for example, rational Cherednik algebras or symplectic reflection algebras, or so-called finite W algebras, which are obtained by reduction from enveloping algebras. In these finite W algebras, their finite dimensional representations correspond to primitive ideals in the universal enveloping algebras. And it has to do with representations of complex Lie groups regarded as real groups. So this is a statement that we would like to know. Of course, we would like to have a bound on the number of representations and ideally have a description of them. But this is the first thing we want to know, and that's one of the applications. So let me explain the proof of this theorem using the why it is a corollary of what I said about Poisson traces. So well, basically, so we will prove that the quotient of A by its commutator is finite dimensional. And this is sufficient for this theorem because, so this suffices because characters of irreducible finite dimensional representation are linearly independent linear functions on this space. So it is actually when you start learn representations of finite groups, you learn the theorem that characters of irreducible representations of a finite group are linearly independent. And more generally, it's true for any algebra if you think of characters as linear functionals on this space. So therefore, the number of irreducible representations could not be more than the dimension of this space. But then, we also have, so we need to prove that this space is finite dimensional, the space of quantum traces, I could say. But this space, by some trivial argument with filtrations, is less than or equal than the dimension of A0 divided by the Poisson bracket of A0 with itself. So it is very easy to show. And then this thing is finite by the theorem that I stated before, in the case of finitely many symplectic leaves. Okay, so then, after questions, I will pass to the second part, where I will explain how you can prove finite dimensionality of this space and the related spaces, and that uses D modules. So any questions so far? Okay. So now I will explain the proof. And as I said, the difficulty of understanding this space, which is this quotient here, Poisson traces, lies in the fact that it is not a local object, because this span of the Poisson brackets is just a subspace and not an ideal. And so we want to introduce a local object that will, on one hand, that will nevertheless be related to this quotient space. And so that object is a certain D module that is associated to every Poisson variety. So first of all, I want to remind you something. And unfortunately, since there is not very much time, I will not be able to give an introduction to the theory of D modules. But I will remind something. So if X is any variety, then we can define a D module, which is called D sub X on X. So this is a D module on X. And this is actually a right D module on X. Now, if x is smooth, it is very easy to say what it is. Dx is just the sheaf of differential operators on x. But if x is not smooth, which we unfortunately have to consider because, as I said, most examples are, all the interesting examples are singular, well, let me remind you how you develop the theory of D modules in that case. You can define the ring of differential operators D of x, which is Grothendieck differential operators, in the usual way. Operators of order 0 are functions. Operators of order 1 are those that when you commute them with functions, give functions. Operators of order 2 are those that give operators of order 1 when you commute them with functions, and so on. And you could try to consider modules over this ring, at least for an x being affine. But that turns out to be the wrong thing to do. For example, this ring may be non-Noetherian, and in that case, you will not be able to develop any theory. So that's not the right thing to do. And there are many different ways, several different ways to do the right thing. One of them is the Grothendieck theory of crystals. And the other thing is you use an embedding I of x into a smooth variety. And then you say, that D modules on x is D modules on V, which are set theoretically supported on x. This is correct for smooth varieties because in that case there is a direct image functor, which is an equivalence between the category of D modules on x and the category of D modules on V, which is supported set theoretically on x. And you that is called Cauchy-Juarez theorem, and you adopt it as a definition in the singular case. And then you prove that it is independent on the embedding in the strong sense, which means that the category of D modules on x is well defined. In particular, this dx becomes an object of that category. So what is this dx? So dx is a very simple thing. It is just differential operators on V modulo the right ideal generated by the ideal of x in functions on V. And you can show that it is suitably independent on the choice of this embedding. So this is a well-defined object in your category, which is, so dx represents the functor of global sections. So hom from dx to any right D module M is just global sections of M. The only problem with this object is that it is not projective in general on singular varieties. So this functor is not necessarily exact. So this is the object that I'm going to care about. And then I define, so suppose now that x is Poisson. Then I will define M of x. So this is going to be dx quotient by ham x, where this means Hamiltonian vector fields on x. So what does that mean? This means that I mod out by the right ideal generated by the Hamiltonian vector fields. Maybe I should put it in angle brackets like that. Well, it's easy to see that Hamiltonian vector fields on x act naturally on dx. In fact, you can prove that the endomorphism algebra of dx is the Grothendieck differential operators, and Hamiltonian vector fields are part of that, so they act. But there are also other ways to define it, which are equivalent. Namely, you can take dv, and you mod out by what I will call jx. If you think of D modules on x as D modules on V supported on x, then you can write it in this way, where gx is the right ideal generated by functions vanishing on x functions on V vanishing on X, and vector fields on V tangent to X, and specializing on X. Well, if you have a vector field tangent to X, then you can specialize it to a vector field on X. And it's specializing on X to a Hamiltonian field. So this means that it's a vector field, it's a derivation of functions on V, which preserves the ideal of X. And if you mod out by that ideal, it acts on the functions on X. And you want it to act by Poisson bracket with some other function. So this is what this M of X is. So this is a D module on X, right D module on X, which is canonically attached to any Poisson variety. Okay, and so the reason this is relevant to our problem is the following. So first of all, what does this D module have to do with our problem? So there is a proposition, which is very easy. And it says, so that let P be the map of X to a point, then this quotient that we are interested in, OX over OX, OX, is just the direct image without non-derived direct image, P sub, I will call it P sub 0, of M of X. So this direct image functor maps D modules on X to vector spaces. And this is a vector space. And it's very easy to see why this is so. Because what is direct image? Well, so the proof is takes half a line. So what is P0 of M of X? This is simply M of X, tensor product over dx with OX. Well, this is really in the case of smooth X, but in the singular case, you can embed it into V, and this will also work. And so this is dx over Hamiltonian X, tensor product over dx with OX. And so this is just OX over the action of Hamiltonian vector fields, which is exactly this space. This is not an exact functor, but the underived part of it is exactly what we want. And the second proposition that is going to give us the power to prove our results is that if X has finitely many symplectic leaves, then the D module M of X is holonomic. So I remind you that holonomic is means it's small in the sense that its functional dimension equals to the dimension of X. And again, I will sketch the proof. It turns out the proof is not very hard. And it's just, you can see from the definition that, well, you can look at the singular support of this D module. And then singular support of M of X. And I'm going to look at its singular support. I will think of it as a D module on V, where X is embedded into a smooth variety V. So singular support then will be inside cotangent bundle of V. And this is just the disjoint. This is just the union of conormal bundles of symplectic leaves. Well, actually contained in there. And then, well, a conormal bundle of anything has a dimension of V. And this union is finite. This is how we use that there is finitely many symplectic leaves. So that means the union also has the same dimension. It could not have bigger dimension. That's right. It cannot have, in general, if we don't assume that, this is always true, but if we don't assume that there are finitely many symplectic leaves, then there could be then there could be infinitely many elements in this union. And so it could be that each, for example, if dimension of V equals 2, then each conormal bundle will have dimension 2, but the union could have dimension 3, because there would be infinitely many of them. But in the finitely many symplectic leaves case, this cannot happen. And this will have the same dimension as V. So it's holonomic. Okay, and then we can prove...
So I'm only used to statements like that when you have Whitney stratifications. And you were talking about the symplectic leaves give you stratifications, but you never said Whitney or Shapiro have a different kind of stratification, like a mu one or something.
It is the nicest possible one. Okay. It is good enough, which means that the closure of a stratum minus this stratum is a union of other strata.
That's a condition of the frontier, but you need some kind of, well, okay, well, I can ask at the end.
Mm-hmm.
Okay, I'll wait. Please go ahead.
Yeah, so, and then we can prove the theorem about finite dimensionality of this space. So this is proof of the theorem. And it says that we just need to say that the direct image of a holonomic D module is holonomic. So this is actually a theorem from D modules, which is very important, but it's non-trivial. And this somehow all the difficulty is hidden in this theorem. But luckily, this theorem is already known, so we can use it, and we get that the direct image is holonomic. But it's a vector space. What does it mean for a vector space to be holonomic? It just means that it is finite dimensional. I should say that this could be upgraded to prove. I had a theorem about OX over OY OX. So if I want to be in a more general setting where phi from x to y is a finite map, then we can define a D module M phi of x, which is going to be dx over the Hamiltonian vector fields y of x. And by this I mean Hamiltonian vector fields on x, which are defined by functions pulled back from y. So this is Hamiltonian vector fields of functions pulled back from y. So there is a map from x to y, and if I have a function on y, I can pull it back to x, and then I can consider the Hamiltonian vector field defined by that function. And so this is a bigger object than M of x in general. But we can generalize both statements. So in particular, if I want to have OX over OY or x, then this is P0 of M phi of x. And the proof is basically the same. And then the proposition if x has finitely many symplectic leaves and phi is finite, then M phi of x is holonomic. And the proof is similar. In this case, we will have a stratification, but now for each symplectic leaf, it will actually be subdivided into pieces, which we're going to stratify it by the rank of the differential of phi, restricted to the tangent space of the leaf. And that will be a stratification which is finer than the one we had before, but it will still be finite because this map is finite. And therefore, we're going to get a union of conormal bundles of those things, which will still be a Lagrangian subvariety of the right dimension. And so we will get a holonomic D-module. And then the proof of the theorem, which I stated, would be exactly the same. Now I should say that there are some generalizations of this. For example, one can compute the replace this, or you can consider quotients of the form n over OXN, where this thing is a Poisson module. And you can prove that if it's a finitely generated Poisson module, this space is finitely dimensional. And in the proof, you will have to slightly generalize everything. And this actually has some applications to representation theory, where we can consider algebras whose associated gradient is not necessarily commutative, but is finite over its center. This also arises in representation theory. So I will not have time to explain that, but it goes roughly along the same lines. So I guess my time is up, so thank you very much.
Thank you. Are there questions, comments?
Yes.
If x is the closure of a nilpotent orbit, do you have an upper bound in this O sub x over?
Okay. If x what we did with Travis is an upper bound for a slice. If I take an important orbit and I take a slice, constant slice. So then we have, this corresponds to a W algebra. And we have an upper bound for this W algebra, and that's the top cohomology of the Stringer fiber.
Oh.
For closure of an orbit, it might be that it is just one. I have to think about it. Yeah, I mean, yeah, I have to think about it. But I think it could be that it is just one. I mean, what corresponds to it is you take functions on an important cone, and then you mod out by some ideal, yes, which is G invariant. So you have functions on an important cone looks like this: C, G, and then some other stuff, yes. And this is in degree 0, this is in degree 1, and so on. And here there are some representations of G. Now, when you mod out by this ideal, you kill some of those representations, but the others remain. Now, if you take Poisson brackets, even with this G, you get all the all the representations here are non-trivial. So you get all of them back. So the quotient is just one-dimensional. So I think this is just one. So this space is one-dimensional for a closure of an nilpotent orbit. But more interesting problem is slice, and there it has big dimension.
Any other questions before I ask my question? So, okay. When you first said stratification, I assumed you were just speaking fairly loosely, that it was a finite disjoint union of some smooth things. But now it satisfies the condition of the frontier, but to know that it's contained in the union of the conormals, don't you need like a Whitney condition, or Cauchy and Shapiro's, I think they call it a mu, some kind of mu stratification? Or, I mean, basically, and maybe it just follows from the fact that they're leaves, that there's not any vanishing in some directions as you move along a leaf, just because it's a leaf, and so nothing changes as you move from here to here. I mean, you need some other property, right?
Well, I mean, these are locally closed subvarieties, and the closure of each of them is a union of others. So do we need anything else?
Well, yeah. If things change too much along strata, then they'd be contained in kind of an infinite number of. Oh, actually, maybe that's. All you need.
I mean, the reason, so how do you prove that it's a union of conormal bundle? You take the associated graded, so you have the relations. That this is very explicit. The proof is very explicit. You take the associated graded of this D module with respect to the order of filtration.
Right.
And then you get that this is functions on the cotangent bundle modulo some ideal which is explicitly described by generators and relations. And then you prove that the spectrum of that ring is a certain scheme, not reduced, but the zero set of the ideal is the union of conormal bundles.
You should need. Well, yeah. Yeah, I guess that's fine. I'll look at it.
Yes.
I'll think about
Yeah,
it.
yeah. Maybe I was missing something, but I think.
No, I'm sure I'm missing something or something that's obvious, like what I'm worried about follows obviously in this case. So I'll think about it. But there is no claim that stratification satisfies Whitney properties, for instance.
I forgot what this.
Yeah. Okay.
is, so.
Well, that would take a while to explain. We can talk about it.
I mean, for example, the basic example of this stratification is this stratification in the case when a finite group acts.
Right.
And then it's stratification by stabilizers. And that satisfies, for example, all...
Yeah, that satisfies all possible, just,
Or stratification into nilpotent orbits or something like that.
yeah. All right. Well, I can look at this later. I'm not going to define Whitney conditions at the end of the talk. Any other questions or comments? All right, well, thanks again. And,